So our goal today is to determine the distance between 2 points on a coordinate grid. And a coordinate grid is just your XY axis. So given any 2 points, can you find the distance between them? And let's get straight to it. So if we're asked to find the distance between the point -2, -2, and it looks like this one's at 4, 3, there's quite a few different ways we could go about it. One misconception I see is some students think that they can count the diagonals between points and that diagonal is worth 1. But remember, because these are squares on a coordinate grid, the diagonal is worth more than 1. And the Pythagorean theorem kind of guarantees that, because if you take any square, pretend that's a square with me, you have to use your imagination, the diagonal is always going to be longer, because this makes a right triangle. And so A, B, and C, we know that C is always along the side, so it can't be the same as A and B. So we can't count the diagonals. That doesn't really help us out. I mean, we could count the diagonals and multiply by the square root of 2 or something like that. But there's another way we could go about it, and I think this is probably the most common way, and that is to kind of build a right triangle between the 2 points. Sorry about my drawing skills here. It's more like I'm shading. And then when we do that, when we build that right triangle, the hypotenuse would be the distance between the 2 points. So all we need to do is count the length of the leg. So if I was to count the vertical leg here, it'd be 1, 2, 3, 4, 1, 2, 3, 4, 5. So this leg here is 5. This leg here is 1, 2, 3, 4, 5, 6. So this leg here is 6. And so now we just have a situation where we can use the Pythagorean theorem, a squared plus b squared equals c squared, to actually solve for c, or the hypotenuse in this case. We'll call it c. So we'll go about that. So 6 squared plus 5 squared equals c squared, or 36 plus 25. And that comes out to, let's see, what would that be? Would that be 61? I believe it would be, equals c squared. So c is equal to the square root of 61. And we could approximate that on a calculator, right? But there's a handy formula, because you may not always want to have to graph and count. So if you were given the point -2, -2, and the point 4, 3, and you're asked to find the distance between them, you could always just graph them. Look at the leg lengths and use the Pythagorean theorem. That would always work, and there's nothing wrong with that. But there is what's called a distance formula, and it's derived from the Pythagorean theorem. It actually is the Pythagorean theorem, just in a different form. And it's pretty handy because you don't have to graph. You can just plug in the values and it will get you the distance, in this case, the square root of 61. So using the exact same example, I'm going to talk about where that distance formula comes from, and then once you get proficient at using it, it's a pretty quick way to go about it. Before we want to make that connection between the last problem, I do want to talk about how to solve for c, because that's all the distance formula is, really. How would we solve for c? Well, you probably see it. It's just the square root of both sides. So if a squared plus b squared equals c squared, then c is equal to the square root of a squared plus b squared. Just take the square root of both sides. Now, a common misconception I see is some students tend to think that this is a true statement. It's not a true statement. These are being added together. They're two separate terms. And so when you have the addition of two numbers, you can't split them up in the square root. They're two separate numbers. Now, if they're being multiplied together, they're considered kind of the same number. And you can split up the square roots of the factors of a number, but not of the addends of a number. So if this is how we solve for c, if we could come up with a way to make this fit, because we know that c represented the hypotenuse in our last example, if we could come up with a way of making this fit with the coordinate points, then we've got our distance formula. So we already know that the triangle that we drew in this particular problem, we drew a right triangle here, and we attributed the value of c to the hypotenuse, which we said was the distance between the 2 points. And this leg we said was 6. And this leg we said was 5, and we found that it was the distance of the square root of 61. And then we went ahead and solved the Pythagorean theorem for c, so c equaled the square root of a squared plus b squared. So we only have one other thing to do, is we need to make this conducive to coordinate points. So how did we get the number 6 and how did we get the number 5? Well, in this case we counted. How could we do it without counting? Well, if we want to know the difference between I guess you could say the bottom leg there, then we need to know the distance from x is -2 all the way over to x is 4. And if you wanted to know that distance, you could subtract them. So -2 minus 4 is -6. Or 4 minus a -2 is 6. So think about this for a moment. The x value of this point is -2. And the x value of this point is 4. One way to find distances between numbers is to find the absolute value, right? So the absolute value of that subtraction, that's -6 inside, so it's going to pop out 6. And if you were to subtract them the other way and say, okay, 4 minus a -2, you would just end up with a +6 anyways. In this particular case, because we're squaring the value and then taking the square root after we sum it, we don't really need absolute value. Check out what I mean. So if we attributed a, because in this case, let's go ahead and call this 6a, this leg right here, and we wanted to plug this in, how can we make this formula get the number 6 for us? Well, what if we said c equals the square root of the first x value minus the second x value, and it doesn't really matter what subscripts we use, you'll see it differently. I think people start with 2. The way you'll probably see it online is x2 minus x1, or in this case, x minus x1. All we're doing there with the little subscript, if you're not used to seeing that, is differentiating between the x values. So it doesn't matter whether I am using the subscript of 1 for this point or this point, as long as I stay consistent. Actually, in this formula, it doesn't even matter how consistent you stay, because check it out. If I'm going to, this represents the value of a, this subtraction. So I got 6, or 6 in this case. If I'm not worried about the absolute value signs here, so if I just was to rewrite this as, so cross this out, if I was just to say -2 minus 4 equals equals -6, let me fix that. It doesn't matter if I get -6 or +6 because the whole thing has to get squared because a is squared. And -6 times -6 is +36, and 6 times 6 is +36. So that works out pretty nicely. And you're probably, hopefully catching on here, the next one's going to just be the difference of the y's. And the y value here is 3, and the y value here is -2. And so if we subtract those, we get 5, or -5, depending on which order you do them. So y minus y1 squared. So the square root of a squared plus b squared, that's really all this distance formula is. We've just said, all we're doing is we're making a statement that a, let me give myself just a bit more room here. All we're doing is saying that a is equal to x minus x1, and we're saying that b is equal to y minus y1. And again, it doesn't matter if you attribute the letter A or B to the horizontal or the vertical leg. But once you know that, and you know how to solve for C in the Pythagorean Theorem, a squared plus b squared, it's just a simple matter of substitution. So we take that and we put it in the place of A, and we take this and we put it in the place of B, and we get, okay, so the distance between any 2 points is equal to the square root of x minus x1 squared plus y minus y1 squared. All right, now I want to do one more example problem just to make this hopefully even clearer. Let's check it out. You know, it occurred to me before I do an additional example problem, we should test our formula. So we said that c was equal to the square of x minus x1 plus the square of y minus y1. And we should test it, because remember, when we just plotted the points and used the Pythagorean Theorem, we got the square root of 61. So let's see if we get that value now. And we had the points -2, -2, and we were finding the distance from that to 4, 3. So if we were to plug those in, I'm going to make these my just my variables x and y, and I'll go ahead and make this my x1, y1. So when I go ahead and plug those in, c is equal to -2 minus 4 squared, so -2 minus 4, plus -2 minus 3 squared. And so we get c is equal to the square root of -6 squared plus -5 squared. And again, it doesn't matter if they're negatives because they're going to be squared. So this is equal to the square root of 36 plus 25, because negative 5 times negative 5 is positive 25, and same with the negative 6, being positive 36. So C equals the square root of 61. So we just took something that we were using the coordinate grid for and looking at. We were looking at the legs and counting the length of those legs using the Pythagorean Theorem. We just took that and kind of modified it so that we could just plug in points from the grid. And I think this is a cool principle of what math allows us to do. So something like this is very summarized. It's like a formula, so to speak. It's called the distance formula. And I guess I'm not a computer programmer by any means, but in my mind, this is kind of more friendly to computing in the sense that you can put your points directly in, and it kind of, you could go, give a very easy step-by-step process on how to get the correct answer. So if someone was going to program a machine to find the distance between 2 points, it probably wouldn't have the machine, which doesn't think like humans, plot the points and count the legs and use a Pythagorean theorem in that sense. It would probably have them plug in the points into this sort of algorithm, this sort of process, and the computer would pop out a number. And so anytime we're able to take a process or an observation we make in math and summarize it into a formula, I think we make it a bit more computable. And everything in our world now seems to be going in that direction, so it's a really good skill to have. And so here's my challenge to my students who are watching, or to anybody who's watching, but specifically to my students. If you're able to program something to find the distance between 2 points, and you have to show proof that you made it. So you can't just download an app that'll do it for you. If you can make your own app that will find the distance between 2 points, automatically run the calculation for you. You could program an Excel spreadsheet to do this. There's all kinds of ways. If you're able to program a computer of any kind, your phone, to do this, I will let you use that on this unit's test. You can't use it on the semester final because I'm not really in control of those per se. They're very controlled tests, but you could definitely use it for this unit's assessment. So there's a challenge for you, and good luck.